This is the second video in our series on graphing polynomial functions. The next part deals with zeros of a polynomial function. This is an important skill in being able to graph the function. So the zeros of a polynomial function, they're also called roots or solution. That's where the graph crosses the x-axis. The zeros are the values of x for which f of x equals 0. Sounds confusing, but it's not. All we have to do is set the polynomial equal to 0 and solve, because it says the zeros are the values of x for which the function equals 0. So we're going to take this original function and we're going to set it equal to 0 and solve. And you know, if you're going to solve something like this, most probably you're going to use factoring. And this factors as x minus 4 times x minus 2 equals 0. Because it's equal to 0, we can use the zero products property and set each piece equal to 0 like I've done here. And then just solve. Add 4 to both sides here, add 2 to both sides here. We get solutions to this equation of x equals 4 and x equals 2, but don't think about them as solutions, think about them as zeros, and think about it this way. They are where the graph crosses the x-axis. So take a look at the graph. This is the graph of x squared minus 6x plus 8 using a graphing utility, and these two blue dots are my zeros because that's where the graph crossed the x-axis. The reason they are called zeros is because each of these points has a y-coordinate of 0. These points are on the x-axis, so they are something comma 0. This is 4 comma 0, and this one over here is 2 comma 0. So that's where the word 0 came from. It's referring to the y value being 0, which is exactly what we did. We let f of x, which is the same as y, equals 0 when we solve this. And to find the zeros, we're going to put 0 in place of this f of x and solve. To solve this, we're going to factor out a GCF to begin with, take an x out of all of this. We're left with x squared minus x minus 2, which factors into these binomials. So we actually have 3 factors right here, and there's the 3 factors. X equals 0, x minus 2 equals 0, and x plus 1 equals 0. This one is actually already solved. This one, add 2 to both sides and solve, subtract 1 from both sides and solve, and we have these 3 zeros. X equals 0, x equals 2, and x equals negative 1. Let's take a look at what the graph looks like. It's a curve, just like we saw in the first video on graphing, but here's these 3 places where the graph crossed the x-axis, and it's crossing at negative 1, which is right here, crossing at 0, and crossing at 2. Now we're going to, by the end of this video, use these roots to be able to sketch the graph. Right now I'm just showing you where the roots or the zeros are, but soon we're going to put this together with the end behavior like we learned in the first video. Another one, set equal to 0. Factor out a GCF of x, and then factor this, and it factors into 2x plus 1 times x minus 4. And if you have trouble with factoring, go back and look at some of the factoring videos that are already posted. Set each one equal to 0, x equals 0, 2x plus 1 equals 0, and x minus 4 equals 0, and solve each of those. X equals 0 is its own answer. To solve this one, you'll have to use 2 steps, subtract 1 from both sides, divide by 2, and then add 4 to both sides gives us x equals 4. Now, I'm not doing any more graphs right now. I'm just showing you the zeros. And basically, all you're doing to get these answers is setting the function equal to 0, factoring, and then you solve. Same idea, set it equal to 0, factor and solve. This is going to be a different factoring technique. Unlike the last couple ones, there is no GCF, but this has 4 terms. And when you have 4 terms, you need to think about factor by grouping. So look just for the GCF of those 2 terms is x squared. And when you divide by x squared, you get 2x plus 1. Here, the minus in the middle comes down. The GCF between these is 9, but the real GCF is negative 9. And if you divide by negative 9, it changes your signs and gives you 2x plus 1. If you have the same parentheses, then you get to continue factoring. 2x plus 1 comes down, and what goes in the other parentheses would be the coefficients that were in front. But x squared minus 9 will factor further. It's the difference of 2 squares, and we get these 3 factors. Set them each equal to 0 and solve. And we get those 3 zeros or roots. There's our function. Set it equal to 0. Our GCF in this case is a negative x squared. And when we divide each of these by negative x squared, this is what we get in the parentheses. And then this factors as x minus 2 times x minus 2. Set each of those equal to 0. We have negative x squared equal to 0. We have x minus 2 equal to 0. I didn't bother writing x minus 2 equal to 0 again because it's the same identical factor as that one. Finish solving each of these. If negative x squared equals 0, that means x has to equal 0, and that means x equals 2. Now this introduces a new concept, and that is what's called multiplicity of roots or multiplicity of zeros. The zeros can have different multiplicities. 0 has multiplicity 2. Now where am I getting that 2? Right here. Because x squared could be written as x times x. So conceivably I could set that equal to 0, set that equal to 0, and we would end up with 0 written twice. That's why it has multiplicity 2. This is x minus 2 times x minus 2, but I could have thought of it as x minus 2 squared, which means that 0 of 2 is going to also have multiplicity 2. This next one is already in factored form, and there are some in the book that are already in factored form, so that all you have to do is set each piece equal to 0. Set x squared equal to 0, set this part equal to 0, and solve. You're going to get x equal to 0 as one of them, and x equals 4 is the other one. But because these are raised to a power, we have multiplicities that are different. X equals 0, because this has a power of 2, we say 0 has multiplicity 2. Because this has power 3, we say this has multiplicity 3. And all that refers to is, instead of writing it as x minus 4 cubed, I could write out x minus 4 times x minus 4 times x minus 4 3 times. And when I would set those equal to 0 and solve, I would have 4 written down 3 times. Now what this multiplicity has to do with the graph is this. The polynomial function will cross the x-axis at a 0 or root. We've already said that. But if the 0 has even multiplicity, then the graph is going to bounce at that point. If it has a root or 0 with odd multiplicity, it still crosses at that point, but it's going to have a little wiggle to it. You're going to see this happen on some functions in the next video. Let's see if we can put all this together to get a complete graph of a polynomial. There's our original function. Set it equal to 0. Because this has got 4 terms, we need to think about factor by grouping. We can take an x squared out of the front, take a negative 1 out of that, which is what turns the signs here. Then, because we have the same binomial right there, it's going to come down, and then we have x squared minus 1, which is the difference of 2 squares, which factors as x plus 1 times x minus 1. There's my 3 factors. Set each one equal to 0 and solve. Now, I didn't write out the setting equal to 0. You should be able at this point to just look at those factors and change the sign and get those zeros. I place them on the graph. Now, how does that help? Well, we know for sure it has crossed the axis at those 3 points. What does it do between there? Well, that's what we're going to have to figure out. But there's something else we know, and that is the end behavior that we talked about in the previous video. Look at this. This has got an odd power with a positive coefficient. Odd power, positive coefficient, falls left and rises right. So we know what happens at the ends. We just got to figure out what's happening in between here. To figure out what happens in between, we want to do some numbers in a t-chart. So I have my 3 red dots, which are my zeros. I'm going to pick numbers between my zeros. So between negative 1 and 1 is 0. So that's my x value I'm choosing. And between 1 and 3 is the x value 2. So I've already done the arithmetic to find the y value, plug 0 in and got 3, plug 2 in and got negative 3. So that's these blue dots. So if I'm going to connect my dots now, I know that this has got to follow this kind of curve. Just up, cross, back down, and so on. So that's what it looks like completed. Now look at the color coordination here. The red dots were my zeros. The blue was my end behavior that I knew based on that information. Then I picked numbers for my t-chart to figure out what's happening between the zeros. Now here's something that we can't tell. When you get to calculus, you can. Are we certain this is the absolute highest point? No, we're not. There's a possibility it could have gone a little bit higher and then started to fall off there. We're not able to figure that out. We're just going to go with this and hope we're right. Later on in calculus, you'll know ways to figure that out. Here's a few things that can help make your graph more accurate. find the y-intercept. I did find the y-intercept on the last one because 0 was in my t-chart. I didn't call it the y-intercept, but it is. So using 0 in your t-chart, whether it's really between two zeros or not, is a good idea because that gives you your y-intercept. You can also check for symmetry to the y-axis or to the origin. Neither one of those is true. To have y-axis symmetry, it must be an even function. This isn't even. To have origin symmetry, it must be an odd function. This is not an odd function. If you don't remember even and odd, look back at the video on even and odd. So I didn't bother with the symmetry idea. This is something we haven't talked about yet, and that is the maximum number of turnaround points is always one less than the degree of the polynomial. Turnaround refers to reaching a peak and then turning around and going back down to the bottom, turn around and go back up.